Okay, our last lesson in Unit 7 is application problems using exponential models with differential equations. One of the things that we're going to see is a little shortcut. So the lesson's going to teach us how to use exponential functions to model growth and decay in applied problems. And if you hear the statement or read the statement on the AP exam, something that goes along the lines of the rate of change of some quantity y is directly proportional to y, then that can be translated into the differential equation dy dt equals k times y. And when y changes at a rate that's proportional to the amount present, we can translate that or immediately solve that differential equation as y equals some initial constant times e to the kt power. And c is the initial value of y. K is the proportionality constant. When k is positive, we're seeing exponential growth occur. And when k is negative, we see exponential decay occur. There's a typo right there. We'll get that fixed. So let's prove that statement when we see those words. Y changes at a rate, dy dt, that is proportional to the amount that's present. So dy dt, just like our last lesson, we discovered separation of variables was a great technique for solving a general solution. By separating the dy and the y together and the k with the dt together, integrating both sides, we have the natural log of y and kt plus a constant. Then exponentiating both sides, here's that same case. We had that special case earlier in a previous lesson. You can think of e to the kt plus c as e to the kt times e to the c, where we can allow e to the c to be a different constant. I'm going to call it k in this case. No, I don't want to call it k. We've got a k. Let's just call it capital C. So it's going to be capital C instead of a lowercase c. So that gives us y is capital C e to the kt. So we've supported that work by separation of variables procedure to show that the rate of change of y with respect to time is proportional to the amount present y, can also be instantly converted to be y equals ce to the kt using the property of exponents. So let's go look at an example here. Example 2, the rate of change of y is proportional to y. So already we know, let's do this in red here. Whoop. Ah. Well, my pen got crazy. Okay, let's try that again. So we already know that dy dt equals ky is also y equals ce to the kt. And they've given us an initial amount stating that when t is 0, y is 3. So first we want to take the equation, y equals ce to the kt, and solve for c using that initial condition. When y is 3, t is 0, so 0 times k gives us 1, c is 3, and we can use that information. When t is 2, y is 6, our general solution is y equals 3e to the kt. When y is 6, t is 2. So solving for k, we can find our constant of proportionality. Decay is 1/2 natural log of 2. Now I took natural log of both sides and just left that step off. If you use your calculator, that should give you a decimal value, 3466, and so forth. Okay, next we want to write a model for the particular solution. So we know that y is 3e to the natural log. I'm just going to convert this as the square root of 2 times a t. And then solving for our question, what's the value of y when t is 3? So now we can use that model to solve. When t is 3, find y. So this would be a calculator question. Y is 3e to the natural log square root of 2 times 3, and that's roughly 8.485 or 8.486, depending on how you want to round. And just to check out that we've done that correctly, I've got the graph here. So graphically, on example 2, when x is 3, y is 8.486, and you can tell it's very, very close to 8.486. So we can verify that both algebraically and graphically. The next example, the number of bacteria in a culture is growing at a rate, they're telling us the derivative, at a rate of 3,000 e to the 2/5 t per unit of time t. When t is 0, the number of bacteria present is 7,500. We want to find the number present when t is 5. So they've given us, if we use capital B as bacteria, the rate of change of the bacteria with respect to time, they gave us the rate, is 3,000 e to the 2/5 t, separating the dB with the dt, (3,000). Then the bacteria is 3,000 e to the 2t over 5. And if this is u substitution, if u is 2t over 5, then du is 2/5. So we want to balance that with a 5/2, which is where we get the bacteria. 3,000 times 5 divided by 2 is 7,500, and they told us that was the initial amount, 7,500. E to the 2t divided by 5. Need a little more room here. So bacteria, the rate of growth of bacteria. So here's our particular solution. 7,500 e to the 2t divided by 5. We want to know what the bacteria count is at 5 units of time. So 7,500 e to the 2 times 5 divided by 5 would be e squared. And using our calculator, the b of 5 is exactly 7,500 e squared, or 55,417.92 bacteria, or roughly, if we rounded to the next whole number, about 55,000 418 bacteria present when time is 5. They didn't tell us whether that was minutes, hours, weeks. We don't know. Okay, moving on to example 4. A slow economy caused a company's annual revenues to drop from $530,000 in 2008 to $386,000 in 2010. If the revenue is following an exponential pattern of decline, what's the expected revenue in 2013? So first we need a model, and we know that this is being modeled by exponential decay. Y is CE to the KT. We were given some initial information. We know when time is 0, that's 2008. They had 530,000 in revenue. When time is 2, they had 386,000 in revenue. That was in 2010. And we also know that this is our C value right here, 530,000. So we can use that to find the K value in our model. So we have 386,000 is equal to 530,000 e to the 2k. 386 divided by 530 is e to the 2k by taking the natural log of both sides. And dividing by 2. We're going to know our K value. Then on our calculator, that's roughly this value. And it's negative because it's a decline or a decay. And next we want to answer the question, what's the expected revenue in 2013? So 2013 would be 5 years later. Basically, they're asking us to find when t is 5, what's the y value? Find your y value. And we already know our model is y equals 530,000 e to the negative t, and we're substituting 5 in there. So let's go ahead and put that in there when t is 5. And then using our calculator, we know that it's roughly $239,913.16. This is the expected revenue for 2013. And lots of businesses were experiencing those kind of downturns in the economy during that 2008 period to 2013. Okay, looking ahead to example 5. Suppose you have a population of insects that are increasing according to the law of exponential growth. There are 130 insects after the 3rd day. So we know y equals CE to the KT. We know after the 3rd day there's 130 insects and 380 insects after the 7th day. So we have 380 insects after the 3rd day. If we set that up, we can use substitution. 130 is CE to the 3K. And then also 380 is CE to the 7K. We can treat that like a system of equations and solve for C and then substitute to find K. So first we set up a system of equations. We're going to solve for C and substitute to find K. So if they're both equal to C, 130 is CE to the 3K. C is 130 e to the negative 3K. And 380, using the second equation, we'll call this equation 1, and this one equation 2. So I used equation 1 and isolated C. Now I'm going to substitute into the second equation. 380 is C e to the 7K. And then isolating to solve for K. A little more room here. 380 divided by 130 is e to the 4K, and the bases are the same. Keep the base, add the exponent, can divide through by 10, and take the natural log of both sides. So the natural log of 38 over 13 is equal to 4K. Solving for K, that's 1/4 of the natural log of 38 over 13. So that's roughly 0.268159 on our calculator. So we know a constant of variation. We're going to use that constant of variation to create a growth model. So we want a growth model. That's equation step 4. So here's our model. Which is y equals CE to the 0.268159 t. And when t is 3, when t equals 3, we have, we have 130. So I'm pulling that from a previous equation. Y is 130 when t is 3. CE to the 0.268159 times 3. And solving for C, we have 130 divided by E. 3 times 0.268 is 0.80448. And our C becomes about 58 insects. So initially, there were about 58 insects. The prompt was asking us to find how many insects were in the initial population. Can't spell insects today. INSECTS initially. My pen on my tablet's not working so great. Okay, a couple more examples, 2 more to go. These are all about half-life. So one way you can find half-life is if you have our model y equals ce to the kt, where a sub t is a final amount and a sub naught is an initial amount, then the half-life of the amount is going to be the natural log of 2 divided by k. So in this example, a zircon sample contains 4,000 atoms of the radioactive element 235U. If we're given that 235U has a half-life of 700 million years, how long would it take to decay to 125 atoms? That's our problem. We know we have y equals ce to the kt, or a of t is a sub naught e to the kt. Both are the same equation, just different variables. We know 2,000 equals 4,000 e to the 700 million years. So let's say we started off with 4,000. Half of that would be 2,000. Dividing through here, then we have 1/2 is e to the 700k. So k, taking the natural log of both sides, k is the natural log of 1/2 divided by 700. So let's stop for a minute and think about the properties of natural log so you can see where that formula came from. You know, when you have a natural log of 1/2, that can be rewritten as the natural log of 1 minus the natural log of 2. Well, and the natural log of 1 is 0, goes to 0. So you have negative natural log 2 over that 700, which matches that formula. Natural log of 2 divided by your 700. Or divided by your k, I'm sorry, divided by your k will be your 700. So that's where that formula came from, eliminating that natural log of 1. So using our calculator, the k value turns out to be 0.000990210. There you go. You can say 3. And we want to use this model to solve for our problem. So they're asking us, when will that sample of 4,000 atoms reduce down to 125 atoms? So solving 125 equals 4,000 e to the negative ln 2 over 700. Well, you know, I'm just going to put the decimal there. Negative 3,099,02103 t. I'm solving for t. 125, the natural log of 125 divided by 4,000 I'm taking the natural log of this side. Then dividing with our calculator, natural log of 125 divided by 4,000, all divided by that ugly negative decimal. We're going to get about 3,500. But remember, I'm using 700 to represent millions of years. So in about 3,500 million years, before that zircon degrades to 125 atoms. So it's going to be about 3,500 million years before our zircon sample of 4,000 atoms would be degraded to about 125 atoms. That's an awful long time. So our last example, this is Newton's cooling law. A cup of hot chocolate placed on a table cools at a rate of dH dt is negative 5/100 times the quantity H minus 75 degrees Fahrenheit per minute, where capital H represents the temperature of the hot chocolate and T is time in minutes. If the coffee, that should say chocolate. If the chocolate was at 160 degrees Fahrenheit initially, what will its temperature be 10 minutes later? So we have dH for hot chocolate over dt is negative 5/100 H minus 75. And we want to separate those variables. So dH over H minus 75 is negative 0.5 dt. Integrating both sides, this one's going to be natural log. Scoot this down a little bit. So natural log of H minus 75 is negative 5/100 T plus C. So H minus 75 is exponentiating both sides, actually, using the definition of natural log, is e to the negative 0.05 t plus c. Here's that same situation again, where we can say e to the c is some k. If we let e to the c be some k, then we have h minus 75 is c is our c value, e to the negative 0.05 t. So we know that h of t is 75, adding this 75 to the right side. And what did they tell us at the beginning? That it should be chocolate. When the chocolate was, time was 0, the chocolate temperature was 160. So the C of 0 is 160. And we want to know what the temperature will be 10 minutes later. So if we come back over here and solve for our C, the hot chocolate is 160 minus 75. When that's 0, that's going to be K is 85, if I calculated that correctly. So we got 75 plus 85 e to the negative 0.05 t. And we want to know what that temperature is after 10 minutes later. So again, this is going to be a calculator question. 10 times 100, that's going to move the decimal over. And using our calculator, the hot chocolate 10 minutes later is 126.555 degrees Fahrenheit. So roughly a hot chocolate at 10 minutes, if we round to the next whole number, 127 degrees Fahrenheit. Now, just to mention, unless College Board tells you to round to a whole number, you write 3 decimals accuracy, decimal accuracy for the AP exam. Okay, that finishes up this chapter, Chapter 7, Differential Equations.